So we know that two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. So for finite dimensional vector spaces, dimension completely captures when vector spaces are isomorphic. And this makes checking if things are isomorphic or not isomorphic very straightforward for finite dimensional vector spaces, because we only have to look at their dimension, right? And that's especially nice for a lot of common vector spaces because their dimension is so easy to get. So let's look at some examples. So one example is the span of sine and cosine as a subspace of real valued functions isomorphic to a Euclidean vector space. Well, I mean, all we need to do is ask ourselves, what is the dimension of this span? We have a spanning set, it's sine and cosine. So the question is, are sine and cosine linearly independent? So sine x, cosine x, linearly independent. Well, the answer here is yes, right? Because the equation a1 sine x plus a2 cosine x equals 0. And right, when we write this equals, we mean equals as functions. So right, we're saying that this is supposed to be true for all x. The only way to make these equal for every value of x is for a1 to be 0 and for a2 to be 0. So these are linearly independent. So these two functions, sine and cosine, are a basis for their span. So the dimension of this span is 2. All right, so is this span, this subspace, isomorphic to a Euclidean vector space? Well, it has finite dimension, and there is a Euclidean vector space that has the same dimension, so the answer here is yes. Yes. And we can even say what Euclidean vector space. It's R2, because R2 has the same dimension as the span of sine and cosine. So you can see being able to just look at dimensions is really nice. We never have to explicitly write down an isomorphism because, well, essentially we did already when we proved that equal dimension gives you isomorphic vector spaces. All right, let's look at another example. So to what matrix spaces is P5 isomorphic? So by matrix spaces, I mean spaces that are these spaces. So various choices of M and N. Well, we just need to know about what is isomorphic to what. We just need to know what everything's dimension is. So what is the dimension of M sub Mn? Well, we worked that out before. That's M times N. And what is the dimension of P5? We've worked that out before too. That's 6. Just as a reminder, the dimension, or a basis that can show you that the dimension is 6 is 1x, x squared, x cubed, x to the 4th, and x to the 5th. Right? These clearly span P5. Also, they're clearly linearly independent. There are 6 of them, so P5 has dimension 6. So to answer this question, we just need to know what matrix spaces have dimension 6. Well, so we want to know, how is it possible to choose M and N so that their product is 6? And there are only a few possibilities. We can make a table. Either we could have 1 row and 6 columns, because that would give us a 6-dimensional space, because M times N is going to be 6. We could have 2 rows and 3 columns, 3 rows and 2 columns, or 6 rows and 1 column. So there are exactly 4 matrix spaces, M sub Mn, that are isomorphic to P5. And these are all of them. Of course, if you want a Euclidean space isomorphic to all of these vector spaces, that would just be R6. Right? All of these things have the same dimension, and so they're all isomorphic to each other. Last example, what are the isomorphism classes of subspaces of Rn? So what I'm asking here is what kind of vector spaces, or what isomorphism classes of vector spaces will fit inside of Rn? Well, it's what is the dimension of Rn? Well, it's n, right? We know that already. And we know that all subspaces of Rn have dimension less than or equal to n. We know this because we know that in Rn there can be no more than n linearly independent vectors. So no basis for a subspace can have more than n vectors in it. All right, so the only possibilities for dimensions of subspaces are less than or equal to n. I guess we have to check, are all possibilities less than n represented? Well, remember, in Rn, there's a nice basis. We call it the standard basis, right? That's E1, E2, down to En. Right? E1 is the vector that has a 1 in the first position and zeros elsewhere. E2 is the vector that has a 1 in the second position and zeros elsewhere, all the way down to En, which has zeros everywhere except a 1 in the last position. Right? And if we look at the span of just E1 up through Ek, for some k, what is the dimension of this? This is a subspace. What is the dimension of this subspace? Well, this subspace is spanned by k vectors. These are clearly linearly independent because they're a subset of a linearly independent set. So we have, right, E1 through Ek serve as a basis for their own span, and so the dimension of this span is k. Well, look, by choosing different values for k, we can explicitly produce a subspace of any dimension less than or equal to n. So what are the possible dimensions that fit into Rn? Well, 0, 1, 2, and so on, all the way up to n. In other words, every dimension less than or equal to n is represented, and each of these subspaces, right, span of none of them, which is the zero-dimensional subspace, the span of just the first one, which is a one-dimensional subspace, the span of the first two, which is a two-dimensional subspace, all of these represent the different isomorphism classes that fit inside of Rn because they all have different dimensions, right? There are no other possibilities because there are no other possibilities for isomorphism classes inside of Rn because there are no other possibilities for dimensions that will fit inside of Rn.